let me revise. I think you have forgotten everything. Let me tell you, my dear students, that packing efficiency is the volume covered by particles divided by volume of the unit cell multiplied by 100. Volume of the particle we calculate by using the formula 4 by 3 pi r cube. Volume of unit cell we calculate by using the formula a cube. Now suppose if we need to write out, we will write out the number of particles per unit cell and number of or type of unit cell. So first type of unit cell is FCC. Can you tell me what is the number of particle per unit cell in face centered cubic cell?
4.
Very good. Correct. What is the number of particles present per unit cell in BCC, body centered cubic cell?
2.
2.
What is the number of particles present per unit cell for primitive kind of unit cell?
1.
Very good. What is the number of particles present per unit cell of end-centered cubic cell?
3.
Not 3. It's wrong answer. Think and tell me.
4.
Not even 4. 4 is even a wrong answer. See, this is the end-centered unit cell, and if we have the end-centered unit cell, my dear students, there will be 8 particles at 8 corners. So this is what it is, 1 by 8 multiplied by 8, which gives us 1. And then you have 2 particles at the faces. They should be present at the faces which are the opposite faces. So this is 1 by 2. This is also 1 by 2. That means 1 by 2 multiplied by 2, that is equal to 1. So can you tell me now the total number of particles per unit cell?
2.
Very good. So total number of particles per unit cell in case of the end-centered unit cell is 2. Now I hope, my dear students, you understand it. So volume covered by particles. Now when it comes to the volume covered by particles, for that we can write, if this is n, then for that we will write n multiplied by 4 by 3 pi r cube divided by a cube multiplied by 100. This is what it is, the exact formula for calculating the packing efficiency, and this n are written here. For FCC we take n is equal to 4, for BCC we take n is equal to 2, for primitive we take n is equal to 1, and for end-centered we take n is equal to 2. So using this formula, my dear students, we can easily calculate the packing efficiency, and as we have multiplied it with 100, my dear students, whatever the answer we get, that is what it is, the answer we obtain into the percentage values. So this is the simple way to calculate the packing efficiency, my dear students. Now let's revise the packing efficiency once again for the previous discussions that we have seen. See, in the previous case, that is the case of the packing efficiency for FCC, my dear students, we can easily write it as this. You can see here on the screen, you can see this 4 into 4 by 3 pi r cube divided by a cube. That is what we have written. This 4 is your n for FCC, and the others you are very well aware. And for FCC, my dear students, by doing all these calculations, we find out that the percentage of packing efficiency in face-centered cubic cell, it's 74%. Now, my dear students, we want to study, or we have started studying about the body-centered cubic cell structure into the previous class. When it comes to the body-centered cubic cell structure, my dear students, we can understand this by doing some simple calculations. So let's move forward and understand. See, if you have body-centered cubic cell, then in this particular cubic cell, which is body-centered, you have one particular particle present at the center of the body. So you have one particle which is present at the center of the body. Now we choose two opposite corners. So we have chosen this corner and we have chosen this corner. And when you join this diagonal, which is of the opposite corner, you have 1R, 2R, 3R and 4R. So if you write this and if you give them the points A, B, C, D this way, then you can even have this angle C, which is a 90-degree angle, and you can have this. Now these all are your sides, so you can write A for all of them. This is even A, this is A, this is A, this is A, this is even the A. So now when it comes to finding the DC, my dear students, when this angle is, see, if you look into this triangle, if you look into the triangle CB, I think I have joined it incorrectly. CBD, let us look into the triangle CBD, my dear students. If you look into the triangle CBD, what we can understand here, see, instead of that, let me join this triangle. So we have a triangle C, we have this triangle C as a 90-degree. So this is what it is, your A, and this is even A. So in triangle BCD, you know that your BC square plus CD square is equal to BD square, which is A square plus A square is equal to BD square. That is 2A square is equal to BD square, and therefore BD is equal to square root of 2 into A. So this is what you get is square root of 2 into A. Now if we think about the another triangle, which is this, which is ABD, my dear students, this is your ABD triangle. So when you think about ABD triangle, this AB is equal to A. So in triangle ABD, your AB is equal to A. So you can write AB square plus BD square is equal to AD square, and your AB square is nothing but A square. Your BD square you have seen here, BD square is equal to 2A square. So you can write 2A square is equal to AD square, and A square plus 2A square, that gives you 3A square is equal to AD square. So you get 3A square is equal to AD square, and please remember that your AD is nothing but your 4R. So you can write 3A square is equal to 4R whole square. So that is what I think we have written into the text also. Let us look into that and understand it well. You can see here that we finally get, by doing all this calculation, what we finally get here is this, that we have A square plus 2A square, that is equal to your A square plus 2A square is nothing but that is equal to 3A square, and this 3A square is equal to, or you can say that 3A square is equal to 4R whole square. Now instead of this 4R square, my dear student, I don't know what to use. Instead of this 4R square, my dear student, 4 square, that is 16, and your R square is R, is equal to 3A square. And thus, my dear students, if you write A square, then A square is equal to 16 divided by 3 R square. When you take square root of 16 divided by 3 R square, 16 divided by 3 R square, if you take a square root of it, square root of 16 is 4, square root of 3 is root 3, and square root of R square is R. So you get A is equal to 4 divided by root 3R. Or you can say that R is equal to root 3 by 4A. Now using this value, my dear students, we can find out the packing efficiency. We know that packing efficiency is equal to N into 4 by 3 pi R cube divided by A cube. For BCC, for body center cubic cell, your N is equal to 2. So you can write 2, then 4 by 3 pi R cube. Then you, of course, you need to write multiplied by 100 to get the percentage, divided by A cube. Now your A is equal to, you can see here, you can take the value of A. A is equal to 4 divided by root 3 into R. So you write 4 divided by root 3 into R. So 4 cube is 64. root 3 cube is root 3 into root 3 into root 3. So root 3 into root 3 is 3 and root 3 is root 3. And then my dear student, this r cube we have written. So this r cube and r cube become 1. So r cube divided by r cube is equal to 1. So what you can ultimately, and this 4 2s are 8. This pi we have written. This 3 we have written over here. And we have written 64 down. So finally, by doing all this calculation, my dear students, we get this answer as a 68%. So by doing all this calculation, my dear students, we approximately the packing efficiency for body centered cubic cell is approximately 68%. That is what we get. So packing efficiency for BCC now we have calculated. Now we want to understand the packing efficiency in the simple cubic lattice. To understand, my dear students, this simple cubic lattice, let us understand the structure of the simple cubic lattice. You can see that this is your simple cubic lattice. What I can show you on screen, my dear students. This is a simple cubic lattice. In this simple cubic lattice, my dear students, you have the various spheres which are present in this manner. So here you can write them this way. So here you can say that, my dear students, if this is your A, if you consider it as your A, my dear student, if this is your A, this A is equal to actually 2R, because this is what it is, R. This is the radius of this sphere, and this is the radius of the another sphere. You can see this is even the radius of another sphere. So this is even R, this is even R. So for primitive, you can write A is equal to 2R. So whenever you have the primitive kind of unit cell, for primitive unit cell, you can write A is equal to 2R. Now we know that the packing efficiency is equal to N into 4 by 3 pi R cube divided by A cube. Now for primitive kind of unit cell, your N is equal to 1 by 8 multiplied by 8, because only 8 particles are present at 8 corners. That is equal to 1. So you will write 1. Then you have 4 by 3. Then you have pi R cube. And for A you can write 2R. So it is 2R cube. Ultimately you get 4 multiplied by pi multiplied by R cube divided by 3. 2 cube is equal to 8 and R cube. These R cube and R cube become 1. So we have 3.14 multiplied by 4 divided by 3 into 8. Or you can even simplify it as 3.14, 4 2s are 8 divided by 3.14 divided by 6, my dear students. So when you do this simple calculation, you get certain answer. And let us see what is the final answer that we get. So by doing all these calculations, see, for simple cubic cell, A is equal to 2R. So we put multiplied by 100, 4 by 3 pi R cube into A cube. So 4 into pi into R cube divided by 100, 3 into 2R square, which is 4 multiplied by pi multiplied by R cube multiplied by 100 divided by 3 multiplied by 2. This 4 2s are 8 and R cube. Ultimately, you get 3.14 multiplied by 100 divided by 6, and which ultimately gives you the 52.2% packing efficiency. So my dear students, when you understand these packing efficiencies for the various types of unit cell, what you realize is this. See, you have, okay, one more, we have, you have FCC and your packing efficiency is 74%. If you have BCC, your packing efficiency is 68%. If you have primitive, packing efficiency is 52.2%. That means this is the most efficient way, this is most efficient, we can say. Now, my dear students, this is what it is, the packing efficiency. This is what we calculate out of 100. So, my dear students, if you want to find out the percentage void, if you want to find out percentage void, what we can do, 100 minus 74 is the void. Here 100 minus 68 is the void. Here 100 minus 52.2 is going to be your voids. So can you tell me what could be the void for our FCC?
26.
26 what beta? It's percentage. Okay. Then for BCC, the percentage of void,
32.
32. And for primitive kind of unit cell, what we can say?
47.3.
Very good. Can you repeat again? Can you repeat again?
47.8.
37.3, is it correct?
47.
47.8, I think, because it's 0.2. Am I right? Okay. So this is how, my dear students, you can calculate even the voids easily. So you need not to worry about these things. You can easily calculate the voids. So apart from the packing efficiency, on the base of the packing efficiency, my dear students, you can even calculate the voids. Now calculations involving unit cell dimensions. So let us understand the various dimensions which are involved into the calculations. Let us pay attention and study them well. Let us study them one by one. See, for different calculations, I have done the multiplication also for you, my dear students, whenever it is needed. Suppose there are Z atoms in a unit cell, then Z is equal to 1, it is simple cubic cell. When Z is equal to 2, it is body-centered unit cell. And when Z is equal to 4, it is face-centered cubic close packing, or hexagonal close packing, or we can even call it as a face-centered cubic cell. So this is what you need to remember. If it's better if you remember that during calculation, if you find Z is equal to 1, which is I have written as N is equal to Z is equal to number of particles per unit cell. So here Z represents the number of particles per unit cell. If Z is equal to 1, we have simple cubic unit cell. When Z is equal to 2, we have body-centered cubic unit cell. It may be face-centered, it may be end-centered also. End-centered cubic cell also have Z is equal to 2, and if Z is equal to 4, we can have cubic close packing or hexagonal or face-centered cubic cell. Now if we take 1 mole, we will have Na atoms. Now this is what it is, a very simple idea, my dear students, that the meaning of mole is equal to the Avogadro number. So if we take 1 mole of any substance, when we take 1 mole of any substance, we will have Na atom. Therefore we can say that Na atom is equal to m gram. Now what is your m here? M is equal to either the atomic mass, or we can have the molecular mass. So m is generally atomic mass for the elements and molecular mass for the molecules. So Na atom in m gram, m is actually the molecular mass. So Na atom in n gram, or Na atom is in atomic mass. Therefore Z atom has, what is the mass? Once again, see, Na atom has got m gram. The mass of Na atom is equal to m gram. Therefore the mass of Z atom is equal to, that is what we get, Z multiplied by m divided by Na. This is what we get, and this is what is the mass for the Z atoms. So mass for the Z atom, my dear students, we can easily calculate that the mass for the Z atom is represented by, mass of the Z atom is represented by Z multiplied by m divided by Na, where m is equal to the atomic mass or molecular mass for the substance, and the volume of the unit cell is equal to AQ. Therefore, my dear students, if we want to find out the density of the unit cell, this is the density of the unit cell. Density of the unit cell is equal to mass of the unit cell divided by volume of the unit cell. Mass of the unit cell is represented by Z multiplied by M divided by Na. This is what it represents, the mass. And volume we write as a unit A cube. So this is how we find out the density, and to calculate the density of the unit cell, we use this formula Z into M divided by Na multiplied by A cube. So this is the formula to calculate the density of the unit cell. Now, my dear students, this is something extra. What I'm going to share with you is the packing efficiency of hexagonal structure. Let us read the question. A metallic element crystal in a lattice counting a sequence of a layer AB, 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 any packing of the spheres leaves out voids in the lattice. Calculate its key coordination number, calculates its packing efficiency and percentage by volume of the empty space. What is the meaning of this empty space, my dear students? Empty space is nothing but void. And next one, base area of the unit cell and volume of the unit cell. These all things we need to find out. So you can see that, my dear students, if we arrange the particles into the AB, AB, AB manner, we get hexagonal closed packing. So the given packing that we get, AB, 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 is the three-dimensional closed packing as shown in the given figure. In this arrangement, three atoms are arranged at the body-centered position. You can see these three atoms, 1, 2, and 3, in such a way that it forms equilateral triangle. You can see that this is the equilateral triangle. You can see this. That means all the sides of these triangles are same, and 12 atoms are placed at 12 corners. You can, I'm going to show you these 12 atoms. You can see this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. These are the 12 atoms present at the 12 corners. 6 such unit cells or 2 atoms at the opposite faces. You can see these 2 atoms which are at the opposite faces, 1 and 2. So this is how, my dear students, we understand the structure of the hexagonal cubic unit cell. Now we want to find out the number of atoms per unit cell. So you can see that 1 by 6 into 12. Please look at this, my dear students. This 12, what we can see, they are shared 1 by 6 into it. These 1 and 2 which are present, they are shared, I think, 1 by 2 out of it. So let us look into this, that 1 by 6 into 12, 2 into 1 by 2, and these 3 are completely present inside the hexagonal closed packing. These 3, 1, 2, 3 are completely present inside the hexagonal packing. These 1 and 2 are available 1 by 2, 1 by 2, and these all are available 1 by 6. So my dear students, you can see that 1 by 6 into 12 plus 2 into 1 by 2 plus 3, that is 2 plus 1 plus 3, that is 6 atoms per unit cell. So here, my dear students, for hexagonal closed packing, your Z is equal to 6. That is what you can easily understand. The coordination number is 6 atoms in the same layer, 3 above and 3 under. Total 12 atoms in the contact. So coordination number is equal to 12. Now this is what you need to understand here, my dear students. Actually, this, whatever I have shown, they are actually the big spheres, and as they are the big spheres, we need to understand their layering very well. So, my dear students, let me explain you this very well. Let's think about this particular cell first. So let us study about this first. So this sphere, if it is available, my dear students, it is in contact with 1, 2, 3, 4, 5, and 6. Now it is also in contact with 7, 8, and 9. Now above this, we can also plan above this, my dear students. We can also have few more available in the same manner. This way we can draw them. And that is what it is, again the B layer. So if this is the one, it is in contact with, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and then these are also there to count 10, 11, and 12. So if you think of any of the atom which is present over here, it is there in contact with 12 other atoms, 6 in the same plane, 3 above and 3 under. Please remember, 6 in the same plane, 3 above and 3 under. And this is how, my dear students, we can calculate the coordination number. You can see here, I have written it clearly. The coordination number is, my dear student, the coordination number is 6 atom in the same layer which I have shown you, 3 above and 3 under. That is also 6. So 6 plus 6 gives us 12 atoms, and that is why the coordination number is 12. So this is how, my dear students, we can easily understand the coordination number is 12. Now we want to first find out packing fraction. Now what is the difference between packing fraction and packing efficiency? So while calculating the packing efficiency, we use this formula Z into 4 by 3 pi r cube divided by a cube. This particular portion is known as the packing fraction. This is what it is known as the packing fraction. When we multiply it with 100, we get the answer into the percentage, and it is known as the packing efficiency. So this Z multiplied by 4 by 3 pi r cube divided by a cube is known as your packing fraction. So let us first calculate the packing fraction for this hexagonal closed packing. So let us first calculate the packing fraction, my dear students, and understand it well. Each corner atom would be common to 6 other unit cell. If R is the radius of the each sphere, then we can write packing fraction is equal to Z multiplied by 4 by 3 pi r cube divided by V. Now here we want to find out the volume of the hexagon. Here we can easily understand that Z is equal to 6. Now we want to calculate the volume of the hexagon. Volume of the hexagon is equal to base area multiplied by height. Base area is divided in 6 equilateral triangle having a base. So now, my dear students, if we think about a triangle ABC, AD is perpendicular to BC. D is a midpoint. This D is a midpoint, my dear student, of BC. Therefore, we can write AD square plus BD square. This AD square plus, my dear students, this BD square. AD square plus BD square is equal to AB square, because this is the right angle. So AD square plus BD square is equal to AB square. Now, my dear students, if you do it this way, what you will come to know that this AD square plus BD square is equal to AB square. So this is AB, this is AD, and this is BD. So this is what it is, your A. But if you think of this, then again here in this case, A is equal to 2R you can write. So my dear student, your AB is equal to 2R. Please understand, your AB is equal to 2R. Your BD is half of, this is BD. So this BD is equal to R, and DC is also equal to R. CD is equal to R, BD is equal to R. So we can put, for BD we can write R. You just need to find out this, this length AD. So your AD square plus R square is equal to 2R square. Therefore AD square is equal to 4R square minus R square. Therefore AD square is equal to 3R square, or we can say that AD is equal to square root of 3R. So this value, square root of 3R, you get. This is the value for this length. Now area of triangle. Area of triangle is equal to 1 by 2 base into height. Your 1 by 2 is 1 by 2. Your base is 2R. A is equal to 2R. So your base is 2R. Multiplied by height. Height is your square root of 3R. So it is 1 by 2 multiplied by 2 is equal to 1. So it is root 3R square. This is the area of triangle ABC. So when we calculate this area, we have this area of the triangle ABC. Now we know that R is equal to A by, if A is equal to 2R, therefore R is equal to A by 2, we can write. So R is equal to A by 2 whole square. So we can put R is equal to A by 2. So root 3 into A by 2 whole square, that is root 3 by 4 A square. So my dear students, root 3 by A square we have got. Now we want to calculate something else. As the triangle ABC, where we have to, as we have the same kind of 6 triangles, you can see that 1, 2, 3, 4, 5, 6. So we have such 6 triangles. So we just need to multiply this area, that is root 3 by 4 A square with 6. So when we solve this, my dear students, we find 6, like 2 3s are 6 and 2 2s are, so 3 into root 3 by 2 A square, that is the area of the base of the hexagon. So we have found the area of the base of the hexagon. Now, my dear students, we want to calculate the height. So to calculate the height, my dear students, in the layer of B, if we have, now we want to calculate the height. So in the layer B, if we have, or if we consider, you can see this layer B I am talking about. Please pay attention. This is the layer B I am talking about, dear student. See, this is the layer B I am talking about. Now in this layer B, let us study about it. In the layer B, my dear student, suppose this is your layer B and you have a triangle which is equilateral triangle. So for this equilateral triangle, all the angles are 60 degree. So inside this triangle, let us draw a small line. So this is the 3 different spherical which are joined to each other. We draw this triangle, and inside this triangle, if we draw this kind of line, then this angle is going to be 120 degree. This angle is 60 degree, and this angle is 60 degree. No, this angle is 120 plus 30 plus 30. I made a mistake. So you can see that this angle is going to be 120 degree. So your this angle is 120 degree, this angle is 30 degree, this angle is also going to be 30 degree. But these are the R's, or this length we can call it as R. So this length is your R, my dear students. This is your length, which is R. So this is R, this is even R, this length is R, this length is R, and this length is 2R. This is also R, so this length is going to be 2R. So in this triangle, if you look at, we have this angle 60, this angle is 30, this angle is 30, this angle is 120 degree.